So in the second step, we're gonna do a species balance of the species A at the CSTR. So here we have our CSTR. Entering our CSTR, we have a molar flow rate, the FA0, which is equal to the volumetric flow rate times the concentration of the species A, CA0. Leaving our CSTR, we have the molar flow rate, FA1, which is equal to the volumetric flow rate times the concentration of the species A leaving our system, CA1, which is the one we are currently looking for. So our balance would be done around our reactor. So the change of the species A within our CSTR with respect to time is equal to the entering molar flow rate FA0 minus the exiting molar flow rate FA1 plus the reaction rate of the species A times the volume of the CSTR. And because in the CSTR we have steady state, the change of species A with respect to time is 0 because we have steady state. And the molar flow rate can be written as the volumetric flow rate times our corresponding concentration. So 0 is going to be equal. And we can factor the volumetric flow rate out because it's going to be equal for FA0 and FA1. So CA0 minus CA1 plus the reaction rate of the species A times the volume of our CSTR. So in the next step, we will divide our equation with the volume CSTR. So 0 is going to be equal to the volumetric flow rate divided the volume of the CSTR times the concentration of the species A at the inlet CA0 minus the concentration of the species A leaving our system CA1 plus the reaction rate of species A, and with the volumetric flow rate divided the volume of the CSTR, we can summarize it as 1 divided the mean residence time of the CSTR. So the reaction rate we have given by the task. So our A is going to be equal to negative K times CA1 squared. So 0 is going to be equal to 1 divided tau CSTR times CA0 minus CA1 minus K times CA1 square. So 0 is going to be equal to 1 divided tau CSTR times CA0 minus 1 divided tau CSTR times CA1 minus K times CA1 squared. So let me multiply this equation with -1 and rearrange the equation a little bit. So 0 is going to be equal K times CA1 squared plus 1 divided tau CSTR times CA1 minus CA0 divided tau CSTR. To solve this, let me just remind you of the following. If we have an equation where we have A times x squared plus bx plus c equal to 0. The solution would be x1 and 2. We have two solutions. This would be minus b plus minus the square root of b squared minus 4 times ac divided 2 times a. In our context, the variable x is ca1. The a term is the one in front of ca squared. In our case, this would be k. B is going to be equal to the term in front of ca1 elevated 1. In our case, this will be this term, which is 1 divided tau CSTR. So B is going to be equal to 1 divided tau CSTR. And C is a term which is not related with CA1 directly. So this would be our C term. So C is equal to negative CA0 divided tau CSTR. So we will insert this for our solution, which will result in CA1 being equal to negative B, which is negative 1 divided tau CSTR plus minus square root 1 divided tau CSTR squared minus 4 times A, which is K, times C, which is negative CA0 divided tau CSTR divided 2 times A, which is K. So CA1 is going to be equal to negative 1 divided tau CSTR plus minus square root of 1 divided tau CSTR squared, and minus is positive, so plus 4k CA0 divided tau CSTR divided 2k. So tau is always positive, so this term is negative. And this term is positive. And for this reason, the only solution is if we use plus here instead of minus. So we have a positive CA1. And from our species balance 1 and 2, we have determined following terms. And we have said that the conversion is equal to this concentration of species A at their inlet, CA0, minus the concentration CA2 at our outlet, divided CA0. And we can further simplify it as 1 minus CA2 divided CA0. The CA2 we have here, and we just inserted it here. This is then 1 minus 1 divided K times tau PFR plus 1 divided CA1, and everything here divided with CA0. And for CA1, we have determined this term, and we will insert it here. So conversion of the species A is equal to... Actually, we can simplify this as 1 minus 1 divided CA0 times K tau PFR plus 1 divided CA1. And now we can insert the CA1 term from 2. So the conversion of species A is going to be equal to 1 minus 1 divided CA0, parenthesis K times tau PFR plus 1 divided negative 1 divided tau CSTR plus square root of 1 divided tau CSTR squared plus 4K times CA0 divided tau CSTR, and this divided and this all divided with 2K. And the 2K actually we can bring up here, so it looks a bit more cleaner. So this is our result. I'm sure you can further simplify it, but I will leave it at this. Is at